This video is going to explore reactions that occur when you treat an amine with nitrous acid, and you probably remember from your Gen Chem days that HNO3 is nitric acid, but if we remove an oxygen, we go from nitric to HNO2, which is nitrous acid. And nitrous acid is unstable, and thus treating an amine with nitrous acid means that nitrous acid has to be prepared in the presence of the amine. I mean, if you remember, we call that an in situ preparation. Right? In situ just means in place. And the way that we make the nitrous acid in situ in the presence of the amine is by treating sodium nitrite. So sodium nitrite, you can see down here, NaNO2, is treated with a strong acid like HCl or sulfuric acid. You can see they're using hydrochloric acid here. And under these conditions, the nitrous acid is further protonated, followed by a loss of water to give what's called a nitrosonium ion. So you see the reaction here in the first step between your sodium nitrite and your hydrochloric acid, which makes the nitrous acid, but then it gets protonated and you end up losing water to make this neat ion, which is called a nitrosonium ion. Now you definitely need to know the structure of the nitrosonium ion that's shown here. And you should also know that by virtue of the positive charge that's on it, it's a very strong electrophile and it's subject to nucleophilic attack by any amine that's going to be in the solution. And so an equilibrium is going to be established in which the concentration of the nitrosonium is very small. However, as the nitrosonium ion gets formed, it's going to react with whatever amine is present. Then, according to Le Chatelier's principle, the equilibrium is going to adjust itself to produce more nitrosonium ion. Now, the outcome of the reaction between the amine and the nitrosonium ion is going to depend on whether the amine is primary or secondary. And so we're going to start with a secondary amine, which is the less interesting of the reactions. So when a secondary amine is treated with sodium nitrite in the presence of HCl, remember it makes your nitrosonium ion, so that reacts with the amine, and you form what's called an N-nitrosamine. Now, the formation of the N-nitrosamine is shown down here. So you form your nitrosonium ion, which is your very powerful electrophile. You can see there's a nucleophilic attack on the nitrosonium ion. Then you just do a proton transfer and it's over, and you end up with your N-nitrosamine. And the reason why I said this section wasn't as interesting as when you react a primary amine with a nitrosonium ion is because nitrosamines, first of all, we don't do anything with them in terms of synthesis in this class, but also they're known to be potent carcinogens, and you see some examples here. You see this N-nitrosopyrrolidine that's found in fried bacon, and then this one here, which is a nicotine derivative that's found in tobacco smoke. Now, a reaction that's super cool is the reaction of a primary amine with nitrous acid, because we call that diazotization, and we end up forming what's called a diazonium salt. So you take the primary amine, you treat it with sodium nitrite and HCl, and you get your diazonium salt. And you should know how to draw the Lewis structure of the diazonium salt. You can see there's a lone pair missing here, and of course, the lone pair on the chloride like that. So again, we call this process that you see here, when we make the diazonium salt, it's got a fancy name. It's called diazotization. Now, the mechanism of diazotization is shown here. And you might look at this and say, oh man, this is so difficult, okay? But check it out. You have your nitrosonium ion, you have an amine. Of course, the amine is a nucleophile, and it's going to attack this very powerful electrophile. So once you do that, it's just a bunch of proton transfers, 1, 2, 3 proton transfers. And all you're trying to do is get to a point where you lose water. So you lose water, and then you end up with your diazonium salt. They left out the chloride here. But just like the mechanism of the formation of the nitrosamine, I'm not going to ask you the mechanism of the formation of a diazonium ion. Okay, next question. What can we do with this diazonium ion? Well, if the R group of the primary amine is an alkyl group as opposed to an aryl group, then you get a diazonium salt that's very, very unstable. So if you have an alkyl diazonium, it's extremely unstable and is too reactive to be isolated. It can liberate nitrogen gas to give you a carbocation, which can react via a bunch of different ways. You could also capture the carbocation with water to make an alcohol, or you could lose a proton to form an alkene. But the reaction generates a mixture of products, and therefore it's not really useful to have an alkyl diazonium salt. Also, the expulsion of the nitrogen gas can be explosive. So yeah, we frown on making alkyl diazoniums. On the other hand, though, if our primary amine is aryl, okay, like you see here, an aryl amine, then you end up with an aryl diazonium salt. And an aryl diazonium salt, like you see here, is stable enough to be useful. It doesn't just spontaneously break down to give you nitrogen gas, because the reason it doesn't do that, I shouldn't draw this on here because it's kind of a sin to do so, but it doesn't just liberate nitrogen. This can't happen, so don't write it down, because then you'd end up with an aryl carbocation like that, which is very unstable. So let's just erase that and pretend I didn't even mention that. Okay, so the aryl diazonium salt, like I said, this guy here, an aryl diazonium salt, is going to be extremely useful to do a whole bunch of different reactions where we can replace the diazonium ion with halogens, with a nitrile. We can even make a carboxylic acid. We can convert it to a fluorine, and we're going to see that in our next lecture video.